All right, started recording. Hi, everyone. How are you? It's always so awkward at the very beginning, especially because everybody has their cameras off. So I'm talking to the void. So I know that you have completed your quizzes. I have not had a chance to grade them yet today. My plan is to grade them tomorrow, and then if there are any like commonly missed questions, I'll probably just do a quick video that I'll post in the announcements, going over just, common issues that I saw. So my goal originally was to have them done by our meeting now, but that I didn't get a chance to get those done in time, unfortunately. So the good thing about that, though, is it does give us more time to just focus on the material for homework 3, homework 3.5, and homework 4. So I see a question about where we need to upload our written work for the quiz. So let me show you where that is in Eagle Online one more time. And then we can get into the material, okay? So give me 1 second and I will share my screen. All right, so if we look at the Eagle Online course page, you want to go up to assignments, and then the first section is all the weekly lecture drop boxes. So you need to scroll down until you get, then it's going to be activities and worksheets, and then most likely it's going to stop displaying here. And so you have 2 choices to be able to see the next section. You can either just say next for page 2 of 2, or you can choose right here to adjust this so it shows more results per page. I'm just going to go to the right. And then once you go to the right, then you can get to the drop boxes for the quizzes. So you've got quiz 1. I know that it said it was due last night. It's okay if you upload it today. It'll still let you upload it. Let me know if it doesn't, though, okay? Let's see, any other sort of like managerial questions like that I can answer before I get into the material? If you have questions about specific homework assignments or specific problems from the homework, I'm happy to answer those. I just want to make sure I get through the main material of what I have planned, and then I'm happy to answer questions about homework assignments at the end, okay? So any other kind of like, where do we find stuff? What do we do? Any of those types of questions? Okay. I'm going to change the screen that I'm sharing. Today, like I said, I'm going to talk about stuff from homework 3, homework 3.5, and homework 4. I know the numbering's weird. It just, I don't know, it's weird. I didn't number them. Homework 3 and homework 3.5. Homework 3 and homework 3.5 go together. And so we just haven't fixed the numbering because we share homework assignments across multiple instructors, okay? So the first thing I want to touch on is linear functions. So a relationship F defined by y equals f of x. And so what I want you to see here is this y equals part. F of x is indicating that is the output is a function of the input. So whether you see y equals mx plus b or f of x equals mx plus b, they mean really the same thing. Later on, if you get into more depth in terms of looking at different ways to think about functions, this does become a little more important. But right now we're looking at functions from the standpoint of when you have an output y or f of x, it is dependent on your input x. X is considered our independent variable. So for example, if I had f of x equals 2x plus 3, what that tells us is our input value gets multiplied by 2 and then 3 is added to it. And that final amount is our output, our function of that. So if I said find f of 1, what that means is that we want to let x equal 1, and we're going to plug that in for x and evaluate it. So if we plug that in, we would have, let me change colors. We'd have 2 times 1 plus 3, which 2 times 1 is just 2, and 2 plus 3 is going to equal 5. Therefore, f of 1, f of 1 equals 5, or f of x equals 5 when x equals 1, right? That's kind of what that notation means. And so we're going to be using that function notation a little bit more in the work that we do in 3, 3.5, and 4, okay? So in homework 3 and into homework 3.5, you are going to be solving application problems, application linear equation problems. And some of these application problems consist of a system of equations. And so a really brief review of what we think about with systems of equations. We're dealing with systems of 2 equations, and those 2 equations are linear equations. And so there's 3 different ways that they can intersect with each other. They can come together at one point, which is one solution. It's going to be a single ordered pair right here. Those lines can be parallel, where they're those lines are not going to intersect, or one equation can be a multiple of another equation. Typically, what we are dealing with in homework 3 is systems of linear equations that will have a single solution. So they're going to be intersecting at an ordered pair, okay? So, for example, you will see in the videos, they talk about mixture problems or solution problems. And these are an example of a system of a linear equation. And so in order to solve the problem, we need to write and solve a system of equations. So when dealing with these, we're given information about a solution that we want to make. And so in this case, it says you want to make 1,000 milliliters of a solution with a 25% concentration. Sometimes the problems will talk about it being 25% alcohol concentration, or later if you could be dealing with, especially, we'll see this type of problem come up again when we get to unit 3, unit 2, I forget which unit is our medical unit, but then we talk about creating compound medications based upon 2 different medications that you're using. And so this idea comes back again, which is why we touch on it right now. So you're going to make this solution with this specific concentration. And in order to make that, you're going to combine 2 other solutions. One that has 10% concentration and one that has a 30% concentration. By the way, if you are creating a solution, that resulting percentage has to be between your 2 starting percentages, okay? You can't use 2 concentrations and make something that has a higher percentage concentration from them. It's always going to be in between. And what I mean is you're using one that has 10% and one that has 30%, and thankfully 25% lives between those 2 values. So it says you have access to 2 solutions, and you want to use those to create this 100 milliliter solution. Now, it doesn't tell you how much we're using of each of those, because that's what we're finding, right? So we want the total amount to be 1,000, milliliters, right? Which means we're going to use some amount of our 10%. And some amount of our 30% concentration. Okay. Again, always define your variables. Okay. Defining your variables helps us make sure that we know what we're talking about after we start getting into these calculations, right? So if we think about, if we're using X milliliters of 10% and Y milliliters of 30%, when we combine those together, we want to get our 1,000 milliliters. So we're going to say X plus y equals 1,000. So in our first equation, what we're doing is we are relating the quantities. So we have, again, a certain amount of the 10% plus a certain amount of 30% equals the total amount. Where students will sometimes struggle is then they go, okay, great. Well, what do I do for my second equation? Like what am I supposed to do for the next one? And the next one is going to have to do with the concentrations, okay? So we know that X has 10% concentration. So we're going to say 10% of X plus 30% of Y is equal to 0.25 of 1,000, okay? And so what we're doing in that second equation is we are relating the concentrations to the quantities for each. So we have 10% of our X value plus 30% of our Y value has to equal our final concentration of the final quantity, right? So that's how those values are coming together. So we're going to simplify. And 0.25 times 1,000 is going to give us 250. Okay. Now, what we've done here is we have created a system of two equations, right? We need to solve those. So again, just to reiterate, these are our two equations. This is our system. Now, there's a number of different ways that we can solve this, and I'll show you how you can check it graphically, but we're going to solve this algebraically. And the easiest way to do it is just to use what we call substitution. So we're going to isolate a variable in one of our equations, substitute it in to the other equation, and solve from there. So I choose the top equation because that one's the easiest, right? There's nothing multiplying in front of our variables. It's easier to just isolate. So if I isolate y, that happens by subtracting x from both sides. So I'm going to say y equals 1,000 minus x. So from here, I'm going to take this and plug it in, right? So that gives me 0.1x plus 0.3 times 1,000 minus x equals 250. So what I want you to do is I'm going to let you solve for x. Go ahead and finish this and solve for x and send me your answer in a direct message, please. Okay, so when we have this 0.3 in front, we want to distribute this through. Okay, so that means we're going to multiply both terms by it. So we've got 0.1x plus 0.3 times 1000 minus 0.3 times x equals 250. Make sure you are distributing that 0.3 to both terms. It's a very easy mistake to forget the second term there, right? So continuing to simplify, I've got 0.1x plus, and then 0.3 times 1000 is going to be 300 minus 0.3x equals 250. 0.1x minus 0.3x is going to be negative 0.2x. And I'm running out of room. So subtracting 300 from both sides, we get negative 0.2x equals negative 50, which means I'm going up here, x equals 250 milliliters, right? So we need 250 milliliters of, and this is where it's really important to have defined your variables, right? Defining your variables first tells you, oh yeah, what did x even represent? Well, we need 250 milliliters of the 10% concentration, which if we subtract 250 from 1000, that tells us we need 750 milliliters of the 30% concentration. And a way that you can monitor the reasonableness of your answer is looking at your ending concentration. What do we want our final answer to be at? And then comparing that to your two starting concentrations, right? So I started with 10 and I started with 30. Well, my ending value of 25% is closer to the 30%, which tells us that we need to use more of that 30% than we do of the 10%. So looking at our answers, 750 is much more than 250, right? So we would expect our answer to come out with more of that 30% concentration than of that 10% concentration. Now, like I said, there is a way you can check your answer via graphing it. So I'm going to minimize, make this a little bit smaller so I can pull over my graphing window from Desmos. So give me 1 second to adjust everything. Make a new window so we can see it all at once. Okay, so looking at our relationships, right? We have our two equations right here, right? We've got this one and we have this one. So if we go to Desmos and we type those equations in, I'm going to have x plus y equals 1000. And I know that it is not showing, so we got to zoom way out so we can see our line. There it is, okay? So we have x plus y equals 1000, okay? And then our second one is going to be 0.1x plus 0.3y equals 250. And once we graph those, coming over here, if I hover over, right? So let's blow this up a little bit. If I hover over where those two intersect, we can see that point right there, that gray dot. And it's showing us the intersection between those two equations happens at 250, 750. And so again, without knowing what our variables represent, we could see that solution and be like, I don't know what that means. But because we first defined our variables, we know that x, 250, that ordered pair, that means the 250 milliliters of the 10% concentration, with 750 being the y coordinate there for the 30% concentration. So where we're going from there is we've have these systems, right? And so now we're going to switch into what we deal with linear regression. Now, in my notes, I have a lot of information including the hand calculations for doing this. Listen to what I'm saying right now. Do not calculate linear regression by hand. I cannot emphasize that enough. We are going to use Desmos, and that is what I want you to do. I do not want to see you doing these by hand because it is a waste of your time, and inevitably you will not come up with the right answer because you will make an error in the calculations. Okay, so I am going to show you what the calculations are, but I don't want you to use them. I want you to follow the steps that I'm going to show you in Desmos. Okay, so first of all, linear regression. This has to do with the idea of curve fitting, which is the process of fitting an algebraic equation to a set of data. And the set, if it appears to be linear, a linear equation can be used to describe the data, and the data that best fits, the line that best fits the data is often referred to as the line of best fit or the least squares line. In order to identify the equation of a line that best fit, that we use a process called linear regression. So with coming up with these models, we have the concept of interpolation, which is where we are looking within the set of data we have and predicting, versus extrapolation, which is where we are using our model to predict a point outside of our set of data. And so we can see the data by looking at a scatter plot. And so we've got this set of data here. I'm going to come over to Desmos and we are going to graph it. So we need to create a table in Desmos. So in order to get a table, I'm going to blow this up so you can see what I'm doing. We're going to do add item, okay? And we're going to go down to table, okay? And so I know that my table is horizontal in my notes and we are adding a vertical table, but again, I'm trying not to waste space. So we're going to add our X values first, which are 1, 2, 3, 4, and 5. Okay, and then we will go and add our Y values. So 1, 3, 4, 3, 4. Now, one thing that's really nice when you're putting in a set of data is you can use this plus, this little like magnifying glass with a plus sign in it. This, when you click that zoom fit, it will take you directly to your data on the graph so that you can see it. Okay, so we can see that our data is a cluster. It seems to be increasing as it moves to the right, but maybe there's a line to it, maybe not, right? So the drawing I have here on our notes has to do with the idea of how we come up with this line of best fit algebraically. It has to do with the error of those points from the line that is the average, okay? Again, bunch of stuff I don't expect you to do by hand. I'm just letting you know where it all comes from. So if we try to fit a line through the data points, we'd end up with an error. The error DI is the signed vertical distance between that line. And so it's the perpendicular from the line to that dot, or not perpendicular, so strictly vertical. And if we want to have a line of best fit, we want to minimize that error. But because the error is signed, it's best to work with the sum of it. And then we take the square root after we've squared it. Again, bunch of words that are not really that important in terms of what you are going to be doing, because again, they give you these crazy formulas, right? And this has to do with how we find that error, and it comes up with your slope and your y-intercept, but I don't want you to do these by hand. Again, do not calculate this by hand. Use Desmos, okay? There's also the idea of a correlation coefficient, and this is very important. You'll notice that this is R, right? We don't want R squared, we want R. And when we talk about the correlation coefficient, it is telling us how well our line fits our data. So R is always going to be between -1 and +1. If R is positive, the slope of the least squares line is positive. if r is negative, the slope of the least squares line is negative. The closer the value is to 0, the less of the correlation there is. And if your r is exactly 0, then there is no linear correlation between your data points. So for example, I have in this first one, r equals 0.231. That is pretty close to 0, not great, but again, I wouldn't say that there's a very strong linear correlation. And what that also tells us is how accurate our model is to be able to predict values from. Just like with r equaling 0, we have parabola. That's not linear at all, right? But if we look at these two graphs below, r equals 0.958, those dots are very clearly close to our line, right? That is a tight fit. That's why the number is very close to 1. That is what we would call a strong positive correlation or a strong positive linear correlation. And then in the second one, r is equal to negative 0.961. Again, those data points are very close to our line. And that is a strong negative correlation, a strong negative linear correlation is how we would describe that. So if we go to the next page, we are going to use our data again in order to find the least squares line and the correlation coefficient. So I'm going to show you, I'm going to write out the formula I'm going to put in here first. So what we're going to do is we're going to say y sub 1. And then we use this form, this symbol right here, it's called a tilde, I believe. And on your keyboard, it is on the key to the left of the number 1, right? It's you have to press the shift key in order to get to it. I don't know, do we have it? Let me see if it's listed. It's listed, so if you're using this on your phone and you're like, Aaron, I don't have a what am I trying to say, a keyboard. If you under this little piece and you go to ABC and you click that, you'll see right here you have that tilde sign right there, right? So we can go back to the 1, 2, 3. That's how you can get it as well. Okay, so we're gonna say x1 tilde, and then we're gonna say m x1 plus b. Sorry, so it's y1 tilde m x1 plus b. So if I go over to Desmos, let me just blow this up so y'all can see it a little bit easier. Okay, so I'm gonna type y and then the number 1. It automatically oh, one thing I want to draw your attention to, why am I using y1? And the reason I'm using y1 is because in the table above, it has to correlate. If I'm trying to tell Desmos to do this based upon a set of data, I have to have already put the data in. So the variable that I'm using here has to match the variable that the data list is in, right? So if you're doing multiple datas in here and you've got your data listed in y sub 3, and you go and type in y sub 1 to run linear regression, and you're like, this isn't working, it's because the variable that you're listing here has to match where data is coming from. Okay, so I've got y sub 1, and then we're gonna say, let me just use all the little buttons that y'all would use. There we go. And then we're gonna say m, and then x sub 1 plus b. Okay, so if I hide this keypad, we can see that this blue line is going through those points, right? It has found the average. So what information can we pull from this screen right here? Well, at the bottom, it's listing what they refer to as the parameters. It's giving us our slope and our y-intercept. So we are going to say that y is equal to, again, they list the slope as 0.6 and the b value is 1.2, meaning that is our y-intercept that they found. So we're going to say y equals 0.6x plus 1.2. And then what else do they give us? Well, again, we're not caring about the square of the values. We want the square root, so we're focusing on R. That's our correlation coefficient. So we get an R value equal to 0.7746. Okay, so that is a positive linear correlation. It's not really strong. And so in terms of deciding like how confident we would be, we probably feel pretty confident about generating values within our data set. And what do I mean by within our data set? Let's say I said, find, that's not how you spell what, find y when x is equal to 2.5. So 2.5 would be right here, right? That exists in between 2 and 3. So that would be within our data set, okay? So I'd feel somewhat confident finding that versus in extrapolation is where I'm looking outside. And that would be like find y when x is equal to 10. So that's way out here, right? That's way far out from where our data is. That would be like right, let me see if I can come up with, there we go. So right there is where what our value would be. Oops, hold still, Aaron. And a way that we could find that is if I just said, okay, we'll graph x equaling 10. And that's going to give me my order pair right there. Because I'm looking at what is my y value and my x value is 10. So I graph that line, remember those vertical lines, it's going to give me a y value of 7.2 versus if I said, okay, what about x equaling 2.5? That's here. And so if x equals 2.5, y equals 2.7. So for interpolation, that's when we're looking inside our data and predicting values. Extrapolation is working outside our data and predicting values. So the black line here would be interpolation versus this purple line out here, this value way out here, that's extrapolation. Now with this correlation coefficient, it is close to 1, don't get me wrong, like 0.77, but it's not really close to 1. So I would feel way less confident in terms of extrapolating, moving outside our data with this value. So most of the time, what we're going to be asking you to do with linear regression is applying this concept to a set of data that's not just a line, right? So I have this example here. It says the following table lists the per capita consumption of bottled water in gallons for selected years. And so it says use linear regression to find a linear equation that can be used to predict the per capita consumption of bottled water W in year T, where T is the number of years after 2009. There is a big reason why I'm boxing this. It is very, very important to pay attention to how they're asking you to create the model, okay? In a couple of weeks, you're going to be doing your linear regression project or activity, excuse me, and they're going to ask you to do application stuff like this. And if you are creating a model, but not looking at where they want you to reference your variables from, your model is going to be off. And so what they're saying is that if T is equal to years after 2009, that means in 2009, T equals 0, right? That's what they're trying to tell you. So in order to graph this data, we can't graph it as it is. We have to adjust our years to represent how many years they are since 2009. So 2009, T is going to be 0. 2010, T is 1. 2011, T is 2 because 2011 is 2 years after 2009. 2012, T is 3, in 2013, T is 4. So now we have a set of data that we can graph. So again, this is T, this is going to be W, right? And so what we want to do is we want to go over to Desmos. I'm going to delete out this stuff. And we're going to put in our new data. Now I know that my X values, they're going from 0 to 4. So you can even just, if you're like, I don't want to deal with it, you just delete it. And then you add a new one, right? So now we're dealing with grain stuff. So I'm going to do 0. Green. And then okay, so we've got our data in. Let's zoom fit it. Okay, so we can see that looks pretty straight, right? It clearly has a pretty straight relationship. So again, in terms of judging if your values are going to be reasonable, right? We can see already that this dot is at 27.6. So we're going to expect a y coordinate or a y-intercept, excuse me, that's going to be close to that dot. It might not be exactly that because we are finding the average of that data when we find the line of best fit. We would probably expect this to have a pretty high correlation coefficient because it already looks super linear to begin with. And so those are kind of some things you can keep in mind when monitoring this, okay? So we're going to do, again, checking what is our variable telling us. Well, it's y sub 1 for this column. So we know that when we're putting in our commands to run the linear regression, we can use y sub 1. Okay. And we can see from running that, we end up with a W equals, and then what is our slope? Our slope is 1.13 X, not X, right? Got to make sure you use the variables they tell you to use. Okay, and that's another place you'll get marked wrong. Plus 27.32. And what is our correlation coefficient? Well, we come up with a correlation coefficient of 0.9893. Okay. So here's what I want you to do. I want you to see in part B, it says predict the per capita consumption of bottled water in 2015. I want you to go ahead and calculate that and send me your answer in a direct message, please. Okay, so if we're asking for 2015, remember, our model is based on years starting in 2009, right? So how many years since 2009 is 2015? Okay. So again, if you need to write it down, remember T equals years after 2015, right? So if we do 2015 minus 2009, that gives us 6. So we have to let T equal 6 here, right? So then there's two ways we can do that. We can go over to our graph and say, okay, well, let's remember T, X, they mean the same thing. We're going to say, all right, let X equal 6. And if we zoom out, we can see that we get 34.1. So what is this not taking into account? Well, it's not helping us with the idea of where we started. So if we go to, or excuse me, it's not that's the right answer. I apologize. If we think about looking at our model though, okay, if we do W equals and we do 1.13 times 6 plus 27.32, we will also get 34.1 as our answer. Okay. So there's, again, two ways we can go about doing it. We can use Desmos with the graphing aspect and think about how these things are intersecting visually, or we can also do it by algebra. All right, I want to switch gears to the very last piece, which is homework 4, which is when we start getting into the idea of it's module 1B, and that's where we get into the idea of exponential growth versus linear growth. And so I did provide some information here. We're mostly going to be using these different models, and we'll get more into them next week. But so we have the idea of linear growth when a quantity grows by the same absolute amount each unit of time. You'll notice this looks kind of like the slope-intercept equation, right? It's Q equals R times T plus Q sub 0. Q sub 0 is just refers to your initial quantity. And the reason we write the formula this way is that it relates more towards the idea of practical application, right? We have a starting amount and then it's growing by a set amount each time, versus exponential, either growth or decay. It's when a quantity grows or shrinks by the same percentage. And so we've got models here with 1 plus R and 1 minus R. I'm going to focus on this model here, that f of x equals a times b to the x. This is what you're going to see in a lot of your homework problems in homework 4. And then we have the idea of continuous growth, which I'll talk about next week as well. So it does say graph the sets of data to determine if they're linear or exponential. So we are going to just graph this first set of data, which, spoiler alert, is exponential. So if we graph this data, again, we need to put in our x and y's. And then we are going to zoom fit it. And what we can see is this is coming down. And the more we zoom out, you can kind of get the idea that this is a decreasing curve, okay? And so another way that you can see how is this changing in reference to each other has to do with the ratio of these values. So we want to fit an exponential decay model to this. Now, if you think that you have an exponential relationship, you can use exponential regression and to give you an idea of what the model should be. So what that's going to look like is y sub 1 is a times b, and then we want the exponent to be x sub 1. And so you can see that this model clearly fits our data points really well, and it comes up with these values. Now, these values are not as accurate as they can be, but it does give us an idea that this is clearly exponential. It's hitting those values well, right? So we go over to our written work. We want to write an equation that is in the form of f of x equals a times b to the x, right? So what we can do to help us write this is actually use the ordered pairs that are there. So I'm going to say, instead of y, I'm going to say, okay, this is f of x, right? So we know that when x equals 0, f of x is equal to 13. So if we plug those values in, I'm going to get 13 equals a times b to the 0. Now remember, anything to the 0 power, and we talked about this last week, anything to the 0 power is equal to 1. So we can simplify this by saying 13 equals a times 1, which means a is just equal to 13. So we can replace what we have here by saying, all right, well, f of x is equal to 13 times b to the x. So once we have that piece, now we can use a second ordered pair to come up with the next piece, okay? Because we're trying to whittle this down to get rid of the variables that we don't know, right? Like a and b are going to become numbers. X and y need to just be there in general when we find this model. So we're going to say, okay, well, x equals 1 when f of x equals 7.8. So if I plug those values in, I've got f of x. Oops, I'm plugging values in. We don't need f of x anymore. We're going to say 7.8 is equal to 13 times b to the first. Well, anything to the first power is just itself, right? 3 to the first is just 3. -1 to the first is just -1, right? B to the first is just b. So we can simplify that variable as just 7.8 equals 13 times b. Now, if we divide both sides by 13, we get 0.6 is equal to b, and therefore we can now replace that piece in our equation, right, in here. So our final answer is going to be f of x equals 13 times 0.6 to the x. Or you can just write f of x equals 13 times 0.6 to the x. You don't have the extra time sign. So what I'm trying to show you here is I always suggest graphing your data so you can visually see what's happening with it. You can try to fit a curve to it, an exponential curve to it, but then go back and attack it algebraically, because you'll notice these values are not quite what we want them to be, right? We can see here they came up with 13.0047 and we want 13 versus 0.559324, which is really 0.6. Okay. All right. That was a lot. We did a ton of stuff. In terms of the second set of data is linear. And once you graph that, you can come up with an equation based upon your two ordered pairs. So Katrina, to answer to my access to my slides, are you talking about my handwritten notes? Is that what you're saying? Or the worksheet that I used? The worksheet. Okay, so the blank version of the worksheet is in Eagle Online. So let me show that to you again, in case people forgot where that's at. So in order to find those, and that's also where you will find the recording of this lecture once it's done. So if we go over into Eagle Online and we go to content, and we go to weekly lecture, worksheets right here, you'll notice, here's all the stuff for week 1. So the first thing is the blank note page, the video. So once the video is done, it gets inserted in between, and then the submission box. So for today, all that's listed so far is the blank notes for our lecture plus the submission box. Once this video processes and I'm able to upload it, which honestly takes like a day sometimes. Like I have to wait for Zoom to process it and then send it to me, and then I have to download it and upload it to YouTube. It's a whole thing. But once it's done, I will load it here in between those two things. So Wednesday evening, my goal is always to have the lecture notes uploaded by Wednesday evening so that you have them for the next day. Obviously I always try to be earlier than that, but it doesn't always work. But here is the blank version. So if you wanted to print it out before lecture and just write on it, or if you want to go back and watch the lecture and write everything down again, which is really helpful for studying. Now, what am I trying to say? One warning, right? The Erin warning is that these lectures are never made in a sense that it's going to replace all the videos and all of those things, those resources that are on Eagle Online. But I have found over teaching this course many times, there are certain things that people have a harder time learning from those lectures, and I like to reinforce that. So I don't want you to ever leave this session and be like, well, she never even talked about this. How am I going to know how to do it? You want to go through and still look at the content that we have in Eagle Online before you're getting into your homework assignments, okay? Or if you get into your homework assignments and you're like, I don't know how to do this, you want to go back to the Eagle Online content and remember within the modules at the bottom, I have that additional folder that says additional practice and videos. So you may want to go deeper into some of the stuff that we have. I don't like to release all of it at once because I find students get really overwhelmed if they have too many things to watch. So we have like a core set of videos that we suggest watching. And then if you still have more questions, then there's that additional stuff, but then always email me and I'm happy to jump on a Zoom with you or to make an appointment to jump on a Zoom, right? I have office hours, like I want you to use them. And so if you're, and I've got links to those office hours in Eagle Online. So remember my office hours, I have one Monday from 8 a.m. to 10 a.m., Wednesday at 9 a.m. and Thursday at 11 a.m. But again, if those are not working for you, email me and we'll come up with time to meet, okay? All right, so that is my main lecture. I'm going to stop recording now so that if anybody has homework questions and wants to stay after, I can continue to answer those. But then they're not recorded as part of this lecture, okay?